Swayam Prabha. Digital India. Educated India.
In the third lecture of the course, we will start with characterization of the flow regimes. In the earlier lecture, you may recall that we had discussed a little bit about basic thermodynamics, we had discussed a little bit about both isentropic and non-isentropic processes, and we discussed about shock waves. In this lecture, we will talk about flow through converging diverging nozzle and the flow that occurs within a supersonic blow down type wind tunnel. We will talk about flow over a thin lifting surface like an airfoil over a range of Mach numbers, and that will lead the discussion into a brief discussion of characteristics of hypersonic flow. So, till now most of the discussion has hovered around supersonic flow and its characteristics. In this lecture, we gradually try to take it closer to hypersonic flow and its characteristics too. And as we discuss about it, recall about the lecture 1 contents, where also we had talked about transition from supersonic to hypersonic, looking at the kind of changes that happen as we move from supersonic to hypersonic. What are those changes? Why are those changes happening, and so on. And over the next several weeks, we will keep trying to answer those questions, the what and why of the changes as the discussion matures. We begin with a recapitulation of important relations for isentropic flow through CD nozzles. As you know that in compressible flows, converging diverging nozzles are abundantly found in different kinds of applications, and the area velocity relation and the A by A star relations are a part and parcel of such discussion. So, from the area velocity relation, for example, we know that in the subsonic part of the flow through a CD nozzle, the area decreases and velocity increases, and vice versa. In the supersonic part, area increases and velocity increases, and vice versa. And we are also able to come to the A by A star relation, which gives us the scaling of the area of any section of the CD nozzle with respect to the throat area based on the Mach number of the local Mach number of the flow at that particular area A. And we also define a M star based on the A star property, and we have tried explaining all these things conceptually in the form of simple sketches here. Some more important relations related to choked flow through a CD nozzle, which you should be able to recall, I am sure. And as you see these equations, I think you are able to recall that it's a very important thing to remember that under what conditions the flow is choked in a CD nozzle, and if it is choked, then it is allowing the highest possible mass flow rate that it can under those conditions. And it is important for us to find out what are the corresponding static pressure, the static temperature, etc., how they scale with respect to the stagnation values P naught or T naught when we look at the stagnation chamber conditions. So, these are things which you I expect you have studied in your earlier courses on compressible flow, but if you haven't, then it is a good time to recapitulate all this, and we will also try to come back to these relations whenever possible in the subsequent weeks also, whenever we are discussing them. in some context. Let's move on to some sketches which are kind of self-explanatory, where we try to see variation of Mach number, variation of pressure in the form of a ratio, static pressure of a certain location of the CD nozzle with respect to the stagnation pressure, the Mach number, the local Mach number, and so on. And as you can figure out that this is basically the throat where the flow becomes sonic if it is choked, and the pressure in the form of ratio, it becomes 0.528 exactly. And then based on what kind of back pressures are maintained outside the exit of the CD nozzle, different kinds of conditions may be created which are either isentropic or non-isentropic in the diverging part of the CD nozzle. As you can see, the effect of variation of back pressure can create a lot of situations. You can begin with an under expanded flow which expands beyond the nozzle, where the pressure is even lower than the ideal expanded nozzle, and you have an isentropic flow all through. You have expansion fans created at the lip of the CD nozzle exit, and then as you start raising the back pressure, you come to the ideally expanded pressure, and then if you keep raising it beyond that, gradually oblique shock will form at the exit of the CD nozzle, and it's kind of an over expanded flow in that case. And then there is a normal shock which comes and sits at the exit of the tunnel, and then if you raise the back pressure further, the oblique shock can get into the diverging part, and then there is a normal shock which is formed in the diverging part of the nozzle. So these are different situations which may be created inside the CD nozzle, and if you do have a normal shock, then immediately the flow from supersonic condition through a jump will drop to a subsonic condition and then decelerate further. So these are very important concepts in connection with the CD nozzle. And if you are looking at a supersonic wind tunnel, let's say of the blowdown kind, here is a very simple sketch of an intermittent blowdown tunnel. The CD nozzle will find its application there too. So you have a compressor followed by a dryer, then a storage tank followed by gate valve, pressure regulator, then a settling chamber with a wide angle diffuser usually upstream of it, followed by the CD nozzle, and then the test section where the model is usually kept with some optical axis which is given by the circular portion which is indicating the optical axis, and then the second throat and the subsonic diffuser. So this is basically the schematic of the intermittent blowdown tunnel that we are talking about, and much of the experiments in the supersonic world is conducted in tunnels of this kind. And in order to perform different kinds of experiments in these kind of tunnels, flow visualization may be used. We can think about using balances to measure forces and moments, pressure transducers to measure pressure distribution on models, and so on. A typical optical flow visualization technique that you may use in high speed flows, which is not necessarily confined to supersonic flows, is the Schlieren technique. It is based on density gradient, and it is sensitive to the first derivative of the density, where you can see in one of these pictures a Schlieren flow visualization of a sharp edged conical object placed in a supersonic flow, and the different regions of the flow through which the wave patterns pass are indicated through the different shades which emerge from the Schlieren flow visualization. And this diagram kind of explains the way we set up the experimental facility to make it sensitive to the first derivative of density, making use of some optics and a camera or a screen on which we can project the image and so on. And this optics must find its way through the test section. So, the test section should give the necessary optical access and so on. So, you can read up more on these techniques in other places where dedicated references are available, where details of these are available. So, we may be briefly referring about some experimental data in our course. At that time, we may be talking about some flow visualization. So, it is a good time to be familiar with this too. In our earlier lecture, we were talking about the week 3 and week 2 contents of the course. In this lecture, we try to recall about week 4 and week 5. And if you look into week 4, you see governing equations of viscous compressible flow. It is essentially compressible Navier-Stokes equation, which is the bread and butter of this flow regime. And when we try to reduce it for application in the boundary layer context, we have the compressible boundary layer equations. And when we try to analyze the boundary layer equations, we do find that as the free stream Mach number of the flow becomes higher and higher in the supersonic regime, we do find very large temperature increases in the thin boundary layer adjacent to the body. And this is one of the reasons why aerodynamic heating becomes a severe problem as the flow speeds up. So, when we talk about aerodynamic heating, it is basically the conversion of the large kinetic energy in the flow to its internal energy, and the intense effect of this heating shows up in stagnation regions of the body in the boundary layer. And as the upstream Mach number becomes larger and larger, heating becomes more intense due to strong shock waves. So, one reason is strong shock waves, and the other is very intense viscous dissipation, which may be occurring in the boundary layer regions of the flow. In the week 4, we will also be discussing about another kind of interaction which occurs in the shock wave world, which is called as the shock wave boundary layer interaction, which is very abundantly seen in all kinds of compressible flow applications. Since we already talked about aerodynamic heating and briefly mentioned about the source or sources of the heating, in the subsequent week we will start taking the discussion to high temperature gas dynamics, what are its implications, the thermodynamics and chemistry of high temperature gases, and then we will talk about equilibrium chemically reacting gas mixture. Not that under all situations and circumstances equilibrium would exist, but in the beginning we will consider equilibrium, and then we will try to include non-equilibrium effects too in due course. Since we are getting into effects which will increasingly bring in changes in the flow field compared to what we usually deal in the supersonic regime and increasingly push it towards the hypersonic regime, it is a good time to start talking about how all these changes happen if you look at the flow field over a certain geometry. Let us say a very common geometry that we deal with in aerodynamics is an airfoil, and we know right from very low speeds to very high speeds we keep talking about the airfoil, though we specialize its shape as we apply it over a wide range of speed regimes. Usually as it gets speedier, we would definitely play around with its geometry with specific intentions in mind and make it appear more suitable for high speed applications. So, airfoil, we are mentioning it in a generic sense. It is usually a thin lifting surface that we have in mind, and we are trying to look at its behavior over a range of Mach numbers without going into much specifics. So we'll go point by point. The first point mentions that as m infinity approaches unity, that means we are moving from the subsonic side closer to sonic condition, the flow on both the top and bottom surfaces of an airfoil or a thin lifting surface can be supersonic, both terminated by shock waves. They are terminated in shock waves because they have to finally reduce the velocity again back to subsonic conditions. For a reasonably thick airfoil which are aerodynamically efficient at low speeds, when m infinity increases beyond drag divergence Mach number, the local Mach number can reach 1.2 to 1.3 or higher. So here we are talking about m infinity. That basically means the Mach number calculated based on the free stream conditions. The infinity comes from the free stream concept. We mentioned the word drag divergence Mach number, and it would be a nice thing to explore what this means. So this is a little homework for you if you are not familiar with this. So it basically mentions that when m infinity increases beyond that particular Mach number, the local Mach number on the airfoil upper and lower sides can go into the supersonic regime, and consequently the terminating shocks will get increasingly stronger. These shocks can cause severe flow separation due to adverse pressure gradient that they impose on the boundary layer, leading to a very important flow phenomenon called shock wave boundary layer interaction, which we saw as one of the points to be studied in one of the weeks. The significant flow separation leads to large increase in drag. These shocks are weaker in the case of supercritical airfoils by virtue of their most optimized shape for such free stream Mach numbers. So this is another thing which you may have come across earlier, supercritical airfoils, to try reviewing them. But the first bullet point essentially deals with conditions in the high subsonic Mach number ranges. We are not yet talking about free stream Mach numbers which have gone beyond 1. So in the second bullet point we say that if m infinity is increased to slightly above unity, the shock pattern that was forming on the upper and lower surfaces of the airfoil will move to the trailing edge of the airfoil, and a second shock wave would appear upstream of the leading edge, which was never there when the m infinity was below 1. This second shock is called as the bow shock because of its shape, and it is formed ahead of the airfoil and has no contact with the airfoil surface. So it is basically a detached shock. We mentioned about shock standoff distance, if you recall, in the first lecture itself. So that will give you an idea. In the first lecture we had also drawn a shock which looked like a bow. So this kind of bow shock is also formed around bodies with a blunted nose in supersonic and hypersonic flow regimes too. Now if you increase the supersonic Mach number m infinity further, often of the order of 5 or more, the shock wave is formed very close to the surface, and the flow field between the shock and the body becomes extremely hot. The heat could be enough to dissociate or even ionize the gas in hypervelocity regimes. This flow regime, which has several significant differences with lower supersonic Mach numbers, is called hypersonic flow. And as I said, that when we talk about ionization, we also have to involve hypervelocity flows. So in terms of characterization of hypersonic flow, we are once again looking at several points here. Hypersonic aerodynamics is typically associated with high supersonic Mach numbers, and from a mathematical perspective, like transonic flow, we can show that hypersonic flow is also highly nonlinear in nature, and that has its implications in terms of its analysis as well as the aerodynamic behavior that it manifests. These flows are found to occur on reusable space shuttles during atmospheric re-entry. in long-range ballistic missiles which fly through the outer extent of the atmosphere at hypersonic speeds, on rockets at high altitudes, and so on. Flow characteristics change significantly as Mach number becomes large. This we had talked about even in the first lecture, where we were talking about the parameter beta and what happens if the parameter beta becomes larger and larger. So, there is a lot of kinetic energy content in the flow, and a significant part of that would get converted into the internal energy finally, and then it manifests in the form of extremely high heating of the working fluid, and then different energy modes get excited in the fluid, and therefore, there are manifestations which do not occur at lower speeds. Shock waves are formed closer to the body than at supersonic speeds in the hypersonic regime. The thin flow region formed between the shock and the body surface is called as a thin shock layer. Viscous dissipation within this layer is very large at hypersonic speed, which leads to excessive heating of the flow. This heat also gets transferred to the body surface. All the three modes of heat transfer, namely radiative, convective, and conductive, may play a role because of excessively high temperatures. And consequently, to keep the body safe, it must be protected by a heat shield which is often ablative in nature. Due to enormous heating as well as high altitudes where these flows usually occur on the vehicles, on the practical vehicles, whether they are the re-entry kind or missiles which are flying at extremely high altitudes, or space vehicles which are moving out of the Earth's atmosphere and so on, flow density reduces and consequently boundary layer thickens. Therefore, the displacement effect on the outer inviscid flow becomes stronger and in turn leads to substantial modification of pressure distribution on the body. This affects the forces and moments acting on the body, and it can have a significant influence on its stability. So, these are points to be taken note of. These are extremely important points which characterize this regime. At high temperatures, the flow becomes chemically reacting and therefore altering its thermodynamic characteristics. The calorically perfect gas assumption, which is widely used for supersonic flow, breaks down due to the dependence of specific heats on both pressure and temperature in hypersonic conditions. So, you remember in an earlier lecture we were talking about constant values of Cp and Cv. So, that assumption will completely break down here. Complex chemical reactions occur at the body surface if it is coated with an ablative layer for cooling purposes, and that makes it more complicated in the sense that the air is already reacting at the very high temperatures that it is already in addition to the species which are produced due to the chemical reactions in the air. There are species added on to that due to the chemical reactions in the ablative layer. Since the flow is at a high velocity, a fluid particle in the free stream crosses the vehicle length within a very short time. If chemical reactions get completed within this short transit time, they are said to be equilibrium chemical reactions. However, if not, they are said to be non-equilibrium chemical reactions. The equilibrium or non-equilibrium nature of chemical reactions can alter the flow characteristics quite significantly. So, we are talking about time scales here, typical time scales associated with the chemical reactions as well as the flow time. Very often hypersonic vehicles have a blunt nose. Since the surface slope is very large near the nose, close to 90 degrees, a curved detached shock called as a bow shock is formed. The portion of the shock near the nose of the body is nearly normal. The distance between the nose of the body and the normal portion of the shock is called as shock standoff distance, which we are kind of familiar now. Since the shock is formed away from the body surface, the enormous heat formation across the shock wave at hypersonic speeds is largely carried away by the flow, and a lesser amount of heat reaches the surface, which is desirable for protecting the surface. Due to the highly curved bow shock, the shock angle changes from point to point along its locus and consequently leads to varying entropy change across it. Because we know the entropy change across a shock wave depends on its strength. A curved shock basically has varying strength along its locus. This leads to the formation of a layer of strong entropy gradient in the flow behind the shock, which wets the body surface. This layer of strong entropy gradient carries considerable amount of vorticity, which interacts strongly with the boundary layer characteristics. These are some more interesting facts to probe, and we were talking at some point about trying to limit the relations that we derive usually for supersonic flows to conditions where the m infinity tends to infinity. So, if we try doing that and we apply normal shock relations for such high Mach number limits, then we find that usually the Mach number downstream of the shock will tend towards a finite value if we assume a value of gamma equal to 1.4. However, in our later discussions we will also show that assuming a constant value of gamma for a very high Mach number is not a very valid assumption. Similarly, if we look at density ratios, we will find that density ratio also becomes a finite number. However, not all such expressions will tend towards finite values. Similarly, the theta beta m relation, which we often talk about in the context of oblique shock waves, will show that the wave angle is very close to the compression angle. Like we said, that supersonic wind tunnel is a very important experimental device for exploring supersonic flows. Similarly, shock tube happens to be one of the very important instrumentations for exploring hypersonic flow fields. There are many others, but for simplicity, for now we are mentioning only shock tube, and for now it is important for us to understand only this, that it is basically a long metallic tube closed at both ends with a diaphragm in the middle, separating a region of high pressure gas from a low pressure one, and these two gases could be two different kinds and maintained at different temperatures with different molecular weights and so on. And at some point when the diaphragm is broken, you have a high velocity flow moving towards one section with a shock moving in front of that, while an expanding flow on the other. And then the kind of phenomena that occur inside the shock tube after diaphragm ruptures helps us to conduct experiments which can match hypersonic conditions. It is not that shock tubes are not used for supersonic studies, but it is more often used for studying hypersonic geometries. In the slides you will find some more details related to shock tube, which you can go through in your spare time. I would mention only one point before closing here, that in order to maximize the incident shock strength for a given diaphragm pressure ratio, the driver gas should be a low molecular weight gas at high temperature, and the driven gas should be a high molecular weight gas at low temperatures. We conclude this lecture by saying that preliminary discussion on flow through converging diverging nozzle and supersonic wind tunnel was done in this lecture. There was a discussion on how flow over a slender lifting surface like an airfoil changes with change in upstream Mach number, and we also discussed some aspects of hypersonic flow in this lecture. So, thank you for patient hearing, and we will continue to discuss these issues at greater length in the subsequent lectures.